Now, we saw that ionization energy was the amount of energy it takes to pull an electron off of an atom in the ground state. And there is only one ionization energy for hydrogen because hydrogen only has one electron to take. You can't take any more from it. If you look at helium, it has atomic number 2, so it has 2 electrons. So for helium, you can do a first ionization. And you can do a second ionization then. To take the second electron off. Now, which one's going to be a bigger number? Or the harder it is to pull the electron off, the bigger the numbers, the bigger the ionization energy is going to be. So is the first ionization energy going to be bigger or the second one? Well, if you think about it, you're pulling an electron away from a +2 charge here. And here you're pulling an electron away from a +1 charge. The second one is going to be higher. It's harder to pull an electron away from something with a higher positive charge on it. So you can generalize a little bit and you can say these higher ionization energies like the second one, are bigger than the first ionization energy. Which makes sense. But you can't have a third ionization energy for helium because it only has 2 electrons. So there is no third ionization energy. How about we look at lithium though? Lithium has 3 electrons. You can have a first ionization energy, a second ionization energy, and a third ionization energy. Now, you see something interesting when you take a look at what these look like. If you look at the first ionization energy, it might have like, if we're going to do a bar graph, it might look like this. The second ionization energy is a huge jump, much, much bigger. Why? Why is there this huge jump going from the first to the second? Is it all that much harder to pull the electron away? Well, it has to do with the electron configuration. If you've got a lithium atom, your electron configuration looks like 1s2, 2s1. This is the helium core here, so you could write that as a helium core. Now when you form an Li+, you're taking off the valence electron. So now you're down to just a helium core. And when you form Li plus 2, you're taking away a core electron. So here you're taking away a valence electron. And here you're taking a core electron away. Now, that explains what's going on up here. And it also gives us an experimental way to count how many valence electrons we've got. Because what we can do is pull the electrons off one at a time, and then when we see this huge jump in ionization energy, we know we've hit the core. let's write that down, because that's important. Very hard. It's very difficult. Why? Because the core is a noble gas configuration, and that's especially stable. And if you're robbing electrons from the core, you're busting up a very stable configuration. And that's not going to happen. So let's see what would happen as we go across the table. If you are looking at lithium, we said, the second ionization energy hits the core. So you see a huge jump in the second ionization energy. Big jump between the first ionization energy and the second ionization energy because you're hitting the core. But with beryllium, you're going to be hitting the core in a different place. How many electrons can you take off? Look at the beryllium configuration. It's got a helium core, and you've got a 2s2 valence shell. So you can take away 2 valence electrons. It's pretty easy. The first and second ionization energies are going to be fairly low. You'd expect the second one to be higher than the first, right? But when you hit the third one, there's a huge jump in ionization energy when you try to take away more than 2. When you try to take away 3, you're dipping into the core. Okay, you can keep going with that. If you look at boron, where are you going to see this huge jump in ionization energy? Well, let's write down the electron configuration for boron. Boron's got a helium core, and it's 2s1, 2s2, 2p1. Okay, we ought to see a fairly low first ionization energy because you're taking this one out. Then these should be not too hard either. They're going to be a little more difficult than this. Because you're taking them out of a lower energy subshell. But when you hit the fourth IE, that's going to be just insane. It's going to be a lot larger because you're dipping into the core when you try to take the fourth electron off. So where you hit that huge jump in ionization energy is where you're dipping into the core. And before that, that's how many valence electrons you have. So you've got 3 valence electrons here in boron, with 1 valence electron a lot easier to take off than the other 2. So I'm asking you to take a look at several different atoms, and I give you the ionization energies for them. And you can decide how many valence electrons each of those has, and then match it up with the identity of the atom. For example, if you saw an atom that had a huge fifth ionization energy compared to the first four. That would mean when you take 5 electrons out, you're dipping into the core. So it would have to be an atom where you have 5 more electrons on top of a core. So, for example, suppose you have a neon core. What has 5 more electrons than that? Sodium, magnesium, aluminum, silicon, phosphorus would have 5 more electrons than a neon core. And when you take out 1, 2, 3, 4, 5, well, if you take out 6 from phosphorus, that's going to dip into the core. Silicon, if you take out 1, you're fine, 2, you're fine, 3, you're fine, 4, you're fine, you're back to the core. But if you try to take out 5, you're dipping into the core. So, how about scandium? Let's see, you're going to have a first ionization energy that will take you there. A second ionization energy will take you there. So that's okay. You're taking off valence. Third ionization energy will take you down there. It's okay. You've taken off all 3 valence electrons now. But if you try to take off another one, there'll be a huge jump because you're dipping down into the core.